I challenge you to a battle of machine learning wits. I accept. Excellent. Each of these glasses holds training data. And this is training set poison. Choose a training set to use machine learning on, and then classify this test image. If you get it wrong, you die! Okay. Give me all of them. It's a 7. Inconceivable! That's right! It seems your poison had no effect. You see, this is no ordinary decision tree learning. This is antidote. Antidote symbolically trains on all the possible datasets, and it proved your poison couldn't have made a difference. Wow.
A study of the learnability of relational properties. This paper introduces the MCML framework for quantifying the learnability of decision trees with respect to entire state space. The performance of ML models is normally evaluated on test dataset. However, discrepancies between samples in test datasets and samples in the entire state space can lead to a false confidence in the performance of ML model. MCML uses differences between the ground truth formulas generated using LY and CNN formulas generated using translation of decision trees to quantify the number of samples in the entire state space on which the decision tree will predict a wrong label. We introduce the idea of quantifying differences between two trained decision tree models and perform a systematic study of learning 16 relational properties. Results show that simple ML models can achieve high performance when evaluated in the common setting of train and test datasets. However, MCML metrics show that the performance can degrade substantially when tested against the entire state space. This shows the usefulness of model counting for quantifying the true performance of ML models.
It's challenging to achieve a trade-off between precision and speed for the widely used numerical programming analysis. For large programs, standard analysis can achieve full precision, but it's very slow. The considered baselines, including heuristics and an existing learning approach, can speed up the standard analysis, but it's imprecise. We introduce Lait, which is both fast and precise. Given a polyhedral drawing operation, Lait removes redundant constraints from the drawing output, speeding up the analysis and usually not compromising precision. The decision process on which constraints to remove is not in advance. The learning procedure analyzes a set of training programs with constraint removal. It obtains a dataset on whether the removed constraints affect the precision. Then a classifier is learned. We show Lait to achieve generalization as it works on different programs. Lait is also generic. It can be applied to different numerical domains, including polyhedra and octagon. For more details, welcome to our talk.